Hi everyone, welcome to yet another discussion on AI and ML for the product leaders. The topic for us that we have chosen is Blackwell FP4. We are going to talk about a new architecture change that came in the GPU from NVIDIA under the name Blackwell. It's basically, we can visualize a change that primarily came from the floating point precision. It's more about precision, performance, and governance. We look into all the section one by one before we need to understand what exactly has brought in after the Blackwell FP4 has been introduced. So the shift is basically in the numerical precision. For many years now, and currently in the market as well, BF16 is the industry standard for any large-scale AI training and inference. Now, with the Blackwell architecture, there is a major change that NVIDIA has introduced a native support for 4-bit floating point precision. This is something not just a smaller data type, but also it's a structural shift because this is something that helps us how we basically look about the AI inference at scale. Because this makes feasible for end user to run the high billion parameter trained model on the less infrastructure. Or in a layman term, we can say it makes it enable to get a precision of 16-bit, that too by using a 4-bit floating point precision for the mathematics or metric calculation done on the inferencing engine hosted on the GPU. In other words, we can simply say we are able to fit the large model in the less infrastructure. So we are saving almost a third of what we were investing on the infrastructure point of view prior to the release of Blackwell. Maybe we can take H100 as the reference for this. From the mathematical perspective, how we can say or what we can say exactly has changed over post the introduction of the Blackwell hardware infrastructure. In case of Blackwell, it is being quantized, fully quantized training. Basically, it's not only covering the weights and the activation quantization that has been a trend in the past, but it has included gradients as well. So it's a combination of weights, activation, and gradients all together that is being fully trained throughout the machine learning pipeline. And this is something natively supported with the Blackwell infrastructure. So there is a very precise and optimization being done so that the smaller 16 element scaling blocks can be fit in to give you the same precision that comes out with the FP16. How does it actually works internally, or what has changed to make it happen? It's like the smarter rounding strategy that came in picture. Basically, the Blackwell employs the split rounding strategy. So in the forward pass, it's basically using deterministic rounding, while backward pass applies the adaptive rounding strategies, allowing a model to learn through the quantization noise. Wherein exactly the reverse or the backward pass is the phase where the actual training is being done for the Blackwell infra. And why does it actually matter from the economics perspective? The economic impact is substantial because Blackwell can reduce operational cost as good as 3 to 5 times as compared to H100 in suitable workloads. However, higher the concurrency, increased effective memory capacity, and the better throughput per token has reshaped the inference economics. So basically, we can say with the Blackwell, throughput has increased, and because it is able to use the GPU to the best of its ability, so GPU utilization has increased, and thus the concurrency and thus the throughput as well. However, this doesn't come with all the profits. There is some cost to bear with that. So what is that? What is the trade-off that's come in picture? That's a governance implication. Now, as we understand, Blackwell is something that is able to support natively to fit the larger model size in the less hardware, so the operational cost comes low. And the other aspect is it's coming low because the batch size has increased, even the L2 cache has been optimized, and we got more throughput. However, it comes at a cost of that there is no governance in the picture at the moment. What do we mean by that? Means we don't have a strategy predefined at the moment that can go on, okay, we don't lose this particular critical input that is being fed to the our machine learning pipeline. One such example we can say, even a minor implementation mistake, such as if we leave with the unutilized tensors, it might propagate with the any not a number values. It's more like a garbage value getting created. So even a small tweak can make this model to behave in a very weird way. So this is very important, that only throughput is not the point here. We need to understand the precision comes with the cost, and that is something, the governance, where we need a validation, a well thought through monitoring, and the numerical safeguards. So the core trade-off, if we talk about what comes in picture, is Blackwell marks a very good transition from the bandwidth perspective, that bandwidth is not at all, or we can say it's not that bottleneck at the moment, because GPU utilization is to at its best at unprecedented values. However, it moves the shift to the governance side. So governance bottlenecks are something that surfaces. The conversation shifts from the kernel optimization to system level control now. We need to have the different layers, or we need to have more predictability, or in other terms, the deterministic SLO, that service level objective we need to define, be it at the input stage when the data has been admission to the system, or be it how the memory is being utilized. We can rephrase it like, we need to go on how the KV cache has been isolated, and how the memory fragmentation works, and how scheduling is something that can set up the priority for not losing the important critical task, because there is no governance at the moment we see, wherein we can segregate these heterogeneous input prompts. And eventually at the decode phase as well, we need a governance, so to ensure that we get the response well within the SLA, and we need not to bear the cost of tail latency, that's P99, because the main priority, if we see here, is like we are able to increase the throughput, but we cannot afford to look down on the P99, that's tail latency. And in overall GPU, this is a groundbreaking change in the GPU era. So we'll not call it a Blackwell GPUs as such per se. We should better we call it a Blackwell era, because this is something has changed the whole dynamics of the how the AI infrastructure is being looked after. However, it comes with the cost of data governance. That would be a question to discuss in the coming days, and would be something we need to thought through as a community on whole. Thanks for being there. So it was something that I guess was good enough for us to get a walkthrough on what exactly the Blackwell has done the change, and how at the high level it's able to give you the high throughput and high concurrency. And also we got a high level glimpse of what are the challenges that surface after the inception of Blackwell GPU. Primarily, governance is something that we need to have in the system to safeguard our interest, along with the increased bandwidth. So potentially the bottleneck is not just confined to the bandwidth as it has been in past, but has shifted towards as a system level, that too for the governance perspective. This is all what I intended to discuss today. I hope that makes sense to all of us, and thanks for being there.